All right, so we're going to do another example, Lagrange multipliers example with two constraints. Didn't have time to do it in class. Now, before I do this example, I wanted to show you a graph of the surface that we worked with in class. So I've got this going here. So there's our surface. And we had our function that we were maximizing was e to the minus xy over 4, and our constraint was the circle x squared plus y squared equals 1. So there's our constraint circle, and this is the interior of the region. So there's our function graphed there. And when we, at the end of the problem, when we found our critical points on the interior of the region, we found that we had a saddle point at 0, 0. So there's our saddle point there, and we found that the function value there was 1. And our maximum and minimum was, our minimum was when we had opposite signs and x and y were plus or minus square root of 2 for x and y. And our minimum values were when we had x and y equals square root of 2 over 2, and they had the same signs. So we have our minimums here and on the other side, and our maximums up here on our constraint, just like we found in the problem, and then in the interior we found a saddle point. So this looks like kind of like a Pringles chip. All right, so let's get to our example with two constraints. So for this particular example, we're talking about the intersection of a cone and a plane. So we want to find the maximum height on the intersection of the cone z squared equals x squared plus y squared, and the plane x plus 2z equals 4. So we have our plane intersecting our cone, and we want to find the maximum height, the highest point on that intersection. Well, we need a function to maximize. So we're maximizing the height. And the height is just our distance above the xy plane. So our function, f of x, y, z, is just z. We're maximizing z. That's how high we are above the xy plane. That's our height. And our constraint, we're going to say that g of x, y, z, our one constraint is going to be the cone, and that function is x squared plus y squared minus z squared, and that equals a constant equals 0. And then our second constraint, h of x, y, z, is our plane, and that is x plus 2z equals 4. So those are our constraints. So this is our objective function. And this is constraint. And this function is a constraint. All right, so now we're ready to start a problem. We're going to use Lagrange multipliers. So we're going to say that del f equals lambda del g plus mu del h. So there's our condition, the conditions that we want to satisfy for our maximum and minimum on this curve of intersection. So we're gonna set our equation up, and we're going to equate components. So let's find our gradients. We have del f. Del f is just going to be k hat. Del h, sorry, do del g first. Del g is going to be 2xi plus 2yj minus 2z k. And del h is just going to be I plus 2k. And this is our equation, and we're going to equate the components of this equation. So for our x component, the x component of del f is 0, so we have 0 equals equals 2 lambda x plus mu. So the x component of our del g is 2x, and our x component of our second constraint is just 1. For our y component, we get 0 from the del f equals 2 lambda y. And this tells us that y has to be 0. Remember, we're saying that our gradients are parallel, and we don't want our scalar multiple to be 0, because then we don't have a vector. So this gives us our y component gives us y equals 0, and our z component. Our z component from del f, we get 1 equals minus 2 lambda z from our del g, and we get a plus 2 mu from our del h. So that's our third equation. And we're going to use these. We already have y equals 0, so we know that we have one of our coordinates. We just need to get our other two. All right, so what we're going to do from here is that we know that on the cone, x squared plus y squared x squared plus y squared minus z squared equals 0. And on the plane, hello. So on our plane, we have x plus 2z equals 4. We know that y equals 0, so I'm going to solve for z here and substitute this in for z. So I get, I'm going to solve for x, and I'm going to eliminate x. So x equals 4 minus 2z. That's going to be a little easier. We know that y equals 0, so I'm going to substitute this in for x on our constraint curve. All of these have to be true at the same time. So I have 4 minus 2z squared plus, we know that y equals 0, so 0 squared minus z squared equals 0. I'm going to square this and simplify, and I get 3z squared minus 16z plus 16 equals 0. This factors. Thankfully, this factors. We get 3z minus 4 for one factor, and z minus 4 for the other factor. So z equals 4/3, or z equals 4. And the reason I chose here to solve for x, one, it's easier, and two, we're trying to maximize z. We're trying to find z. So rather than eliminating z and finding x and then having to substitute, we find z, then we're done. Well, the maximum here is z equals 4. So that's our maximum height. And our minimum height then, the smallest on the constraint, would be 4/3. So the minimum height on the intersection of the cone and the plane would be z equals 4/3. And our point would be -4, 0, 4. So we know z equals 4, we know y equals 0, and we can find that x equals -4. And if we take a look at what this looks like, if we graph these functions, look at the intersection. I have that all set up here as well. So there's our cone and our plane intersecting down here, and we see the intersection. We can kind of see it shaded there, the intersection there. And our maximum is up here at z equals 4. And our minimum would be down here, and z would be 4/3. So that would be our intersection and our surfaces. Z equals 4 over here, and z equals 4/3 down here.